Hi, Peter Rossi here. I just wanted to create this short video to discuss the central limit theorem, a topic we will not have time to cover in class, but I think a very important one. So let's take a look at this. I'll share my screen here. Okay, so what you see here is a few slides I've created to illustrate this. So this video is about the central limit theorem, which is really one of the most remarkable results, certainly the most interesting result in probability theory. And so let me state what it says in a pretty general form of the central limit theorem. It says that sums or averages of not two different random variables, and here's kind of a mouthful, converge in distribution to the normal distribution as the number in the sum or average goes to infinity. So that's quite a mouthful, but what does it really mean? It means if you can take random variables that don't have a normal distribution, they don't even have to come from the same distribution, and add them up and then average them, or you don't necessarily have to average them. It helps for normalization to average them. It's not really important, right? And then look at the distribution that simulate from that distribution, look at its distribution. The distribution will look more and more like the normal distribution as the number of random variables that you're averaging gets larger and larger and larger, which is really amazing, right? You can start with a discrete random variable. You could start with a random variable that only takes on a few different values. And then by averaging it and adding it together, you can make it look more like the continuous normal random variable, right? Now that itself is not that surprising, right? Because when you average, even if you take a random variable that can only take on discrete values, like just a simple one, like 1, 2, 3, and 4, when you average it, you get numbers, you fill in the numbers. You can get 1.5, you can get 3.5, and so on. So the fact that this averaging discrete random variables can make them look more continuous is not so surprising in and of itself. But discrete random variables can be very non-normal in their behavior, in the sense they can exhibit skewness. You can take a skewed random variable, continuous or discrete. Like, for example, the income distribution in the United States, very, very skewed. That's quite a bit a topic of a great deal of discussion, right? Is how so-called inequitable or non-uniform, that's all that means, non-uniform the distribution of income is in the United States. If you average up incomes into an average income and consider larger and larger numbers of people in that average, the average will look less skewed and more symmetric. So the very fact of averaging symmetrizes a distribution, right? Similarly, a very thick-tailed distribution, like, for example, a lot of nature gives us a lot of examples of thick-tailed distributions, or the stock market, for example. The stock market's distribution, stock market has returns or periods of time very similar to what we're living through now, where returns are very large relative to the history of returns. So returns of 10%, a decline of 3%, 10% in a day are very rare events relative to the variability of returns, but occur with a much greater frequency than the normal distribution would indicate. So the normal distribution is not a good distribution for stock returns. However, average returns over many different assets might be normally distributed. In other words, taking something that's thick-tailed and make it thin-tailed. That's sometimes the trait of being thick-tailed is called by statisticians exhibiting kurtosis. So kurtosis is the condition of thick-tailedness. That's Kurtosis, kurtosis. So averaging can get rid of kurtosis. You can even take a multimodal distribution. Remember in class we talked about the distribution of heights, right? That the distribution of heights across students can be thought of as a combination of two separate populations, men and women, and it's possible that the distribution of heights for everyone, for all students, is actually multimodal. even that kind of violation of normality can be essentially eliminated by averaging. Okay. Now remember, this is an asymptotic result, meaning that the number of terms in the sum, the number of random variables being averaged or summed, may have to be very large in order to get rid of it. That's particularly true for the thick-tailed aspects of distributions. It's very hard to get rid of thick-tailedness, but it can be done. The central limit theorem does apply. Okay. Now, some of us have seen a physical representation of the central limit theorem. I don't have one of those with me, but I do want to relate what some people might call a childhood experience. When I was a kid, and for fun, here's a picture of me as a kid. When I was a kid, I used to go to the Museum of Science and Industry on the south side of Chicago, very near where I lived. And at that time, it was free. After school, I would walk over to the museum. They had wonderful exhibits on aspects of science and mathematics, and I really enjoyed myself. Actually, they had the first flight simulator was a physical flight simulator, not an electronic one. And one of the things they had in that exhibit was something that is known as the Galton box, Galton, Galton. Galton is a famous statistician. And what it was, these are typically constructed on a wall. And at the top of the wall is a bin, and it contains balls. And I've drawn that bin circled in red here, containing those little blue dots. Those are supposed to be balls. And at the bottom of the bin is a hopper or a butterfly valve that if you open, lets a ball come out. The balls are dropped down the wall. This display is sandwiched between the wall and a pane of glass, so you can see it. As the ball drops, it confronts an array of dowels or rods that are perpendicular to the wall, and they're shown here by each one of these. Like here's one of them. Here's a rod that's shown by a black dot. In this array, we have 8 rods, columns of rods, and we might have many, many, many rows. Okay, so think about what happens when you drop a ball out of that hopper onto this array of rods. And I've shown here. See this one here, this little blue one there. Now it's going to hit one of those rods eventually, right? Let's say it hits the first one there. Now, what can it do when it hits a rod? It can only do one of two things. It can go left or right. So think of that as just like flipping a coin, right? If you flip a fair coin with equal probability, you'll get a head, equal probability a tail. And you might say, as long as I drop these from I don't skew them in the way I drop them, so the mechanical device that drops the balls, as long as it drops them sort of fairly, so to speak, straight down, then it's really going to be half and half. So how does a ball get over here to the extreme left? It basically has to, every time it hits a rod, it has to go left, right? So essentially, it goes to that leftmost bin only if in this number of trials or number of rows of the rods, it goes left every time. That's like flipping a coin 20 times and getting 10 tails. Similarly, and I've labeled it, I don't know if it's actually the 10th here, it's more like the 8th, sorry, that should be 8. This one over here labeled 8 is right, okay? So obviously, when you toss a coin 20 times or 10 times or 8 times, you rarely get all heads and all tails. That does happen, rare. More frequently, you get some mixture of heads and tails. And what is the distribution of the sum of the number of heads in a certain number of coin tosses? In n coin tosses, it's called the binomial distribution. So this device simulates a binomial version of the central limit theorem, namely that if you simulate from a binomial random variable, and if you'll average things, and it will eventually, a binomial random variable, when you have enough draws or enough tosses or enough trials in the binomial history, will eventually look normal. Okay, and so so what happens is these balls are dropped down, they hit the rods, they deflect either left or right, they go through the whole array of rods, and they end up in one of the bins depicted below with a vertical black lines are delimiting each bin, and each bin will have a separate number of balls in it, which I tried to illustrate by the blue dots in the bins. Those represent the mass of the balls. And they'll do this like 1,000 times, and then they'll recycle it, right? So they'll start dropping the balls back down again. And you'll see that the heights of the balls in the bins are exactly a histogram, right? And the histogram looks very symmetric and look quite like a normal distribution. So I've drawn a crude normal density on top of it to indicate that. If you drop enough balls, and you have enough bins, and you have enough rods, this thing will start to look as close as you'd like to the normal bell curve, as we all like to call it. Okay, so that's one way of understanding. And so Galton himself had constructed one of these devices, and his commentary on it was, this shows in some sense how nature, the way in which nature and are the laws of nature, the laws of probability, construct something orderly out of chaos. So this is a chaotic process in the sense of these dropping. It seems very random, the dropping of these balls, but what comes out at the end is something quite a bit lacking in randomness. That actually is not really correct. In fact, the normal density can be derived as a density which maximizes what's something called entropy, which is a measure of dispersion or randomness in some sense. So Galton had it right in the sense that this is a remarkable result, but I think wrong in the sense of characterizing it as showing order out of chaos. Okay, so we could also obviously do this in R, and let's go to R. So here is the RStudio environment, and this code snippet will be available for you in the lecture notes area. So what I'm going to try to do now is illustrate the application of this with respect to using the Poisson distribution. So I'm not even expecting that you know what the Poisson distribution is. The Poisson distribution is what's called a discrete distribution. It is only on positive numbers, or non-negative numbers, I should say. So let's draw 1,000 Poisson draws. We'll use the R function rpois for R Poisson, and you can see that it has two parameters: the usual n, the number of draws you want to do, and lambda, which is the only parameter of the Poisson family of distributions. And in that family, the lambda parameter represents both the mean and the variance, right? So 3 is the mean and the variance. So I'm going to draw 1,000 of them, and I'm going to use the table function to just give me a table of the frequency of each of the outcomes. So the outcomes, you can see the table results down here in the console window. And the table, they're essentially, you don't see any Poisson values really much more than about 10. Most of them are between around 0 and say 6 or 7. So this is a discrete distribution. If I plot the histogram of it, you can see, if you can't already see, how skewed it is. You see the Poisson distribution here is highly skewed. In other words, basically it bangs up against 0 and then has this big long right tail. So this is a great example of a distribution that is skewed, which is the binomial is not skewed unless the probability parameter is different than a half. But if it's a half, it's not skewed at all. This is a highly skewed distribution and very discrete distribution, and also only positive valued. Okay, so let's simulate the distribution of the sum or the average of a number of different Poisson random variables. I hope everyone can see that, right? So what I'm going to do now is I'm going to consider two situations. One where I draw 10 Poissons and average them. And I'm going to do that. I'm going to simulate the distribution. What does that mean? I'll do that not just once, but I'll do that many, many times. I'm going to do it in this case 100,000 times. So here is the number of samples I'm going to do are 100,000. Each sample is size 10. In other words, I'm going to repeat this experiment of drawing Poissons 10 times, taking the average, recording that value, doing that again, very much as we did in the chapter 2 notes, right? But not for the purpose of illustrating the central limit theorem. I want to compare two situations, one where n equals 10, a sample or sum of, or average rather, of 10 Poissons, with another case where n equals 100. And if the central limit theorem is true, one would guess that it would look more normal when you have 100 than when you have only 10, okay? So let's try that. In order to put those two plots side by side, I'm going to use the graphical parameter mf row. So par is a function that sets graphical parameters, and I am setting now an array of graphs whose row dimension is 1 and its column dimension is 2. So as I paint a sequence of graphs, it'll paint one on the left, one on the right, one on the left, one on the right, keep going until I exit. If I wanted to change that to an array of 4 graphs, 2 columns and 2 rows, I would say 2, 2. Okay, so let's run that, make sure that parameter is set. Now I'm going to use the same ideas that I did before. I'm going to simulate a total of 100,000 times 10 Poisson random variables. I will spray them or populate an array called sims with those results. Each column of that array, each column of sims will be a separate sample. I will apply the mean function to each column, and then I'm going to normalize it. So I'm going to divide by the standard deviation, or actually the standard error. This is my best estimate of it. And I'm going to normalize by subtracting the mean. So I'm going to get something that has a mean of 0 and a standard deviation 1, but is not necessarily normally distributed. The central limit theorem would say that distributions look more normal as I increase the number of random variables being averaged, or in this case, the size n. So let's run it first for the samples of size 10, or averaging 10 Poisson random variables. And you can see it created this matrix of 1 million elements. Means contains 100,000 elements, one for every one of the samples. And I've standardized the means. And now let's plot them using the histogram command. And over here on the rightmost plot is a histogram of the draws of these means standardized. So it has mean 0 and about unit standard deviation. Now, does that look normal? No. No, it doesn't look like normal 0, 1, does it? Normal 0, 1 can't get, this one had ones out there, minus 10, things like that, right? No, that cannot happen. That cannot happen, right? Okay, it just cannot happen. So we have to be, what we're gonna see here, and also notice it's a bit skewed. It skews out to negative values versus positive values, right? Let's compare that with what happens when we increase the number of random variables being averaged. In other words, make the central limit theorem set in. What I mean by set in, increase the number being averaged. Let's do that and plot that on the left-hand, or rather right-hand side. Takes a little bit of time to the calculation. Now look at the right-hand side. The right-hand side, a couple of things. First of all, it's very symmetric. Secondly, it only really goes between at most about -3 or so, +3. The maximum is -4, versus the other situation where it got out to -5 with actually more than once. Right, so you can see what this has done is symmetrized the asymmetric Poisson distribution, right, and reduced the thick tails, made it much more normal, made it much more like the bell curve, and made increasingly thin tails. Now this still has a little bit too thick tails for the normal distribution. We only did 100 of them. The central limit theorem doesn't tell you how many you need to use, and it depends in some sense on how pathological or non-normal the target, the distribution that you're averaging is. If it's very violently non-normal, it may take a very large number of terms for it to effectively turn into normal by the averaging method, but it will eventually do so. Okay, so I hope this video has given everyone some insight into what the central limit theorem is and what it means in terms of a practical sense.